Yeah, so hi everybody. Thanks for coming out and seeing me on a Saturday. As said before, I'm Russell Spitzer. I work at Datastax, and the main thing I work on is Cassandra and Spark and the integration between the two of them. So there is the Datastax Spark Cassandra connector, which is one of our biggest open source components, which basically lets you take your data from Cassandra, you work with it in Spark, and of course take any data that you have access to in Spark and put it back into Cassandra. So in case anyone hasn't used Spark before, just a quick description. Spark is a tool for working with big data. I actually just stole right out of the Apache Hadoop homepage its description of Apache Hadoop because it's basically the exact same description. It's a framework that lets you write applications that do distributed work without having to worry about the nitty-gritty of what happens when something breaks, what happens when a node goes down, how am I actually splitting up my data, and all this kind of stuff. So it kind of takes care of a lot of that for you. So basically, working on your big data using high-level abstractions, things that are very familiar to us when we're working with Scala. So you have a very similar collection API, except instead of a map only working on a single machine, when you map in Spark, it's going to work on as many machines as are in your Spark cluster. So one of the newer additions, although this is not too new anymore, is that Spark's biggest direction now is taking SQL and SQL-like statements and turning that into distributed work. So for example, you might have a select count from some source, which might be in Cassandra, it might be some other database, might even be just an old Oracle store somewhere else. And what it will do is take these rather simple high-level descriptions of what you want to do and turn it into distributed work on whatever your system happens to be. Whether or not you're on the cloud, or your in-home data center, or on your own dev box. Whatever you're doing, it's going to take your little description and change it into a larger distributed computation. So how this happens is a little bit of dark art. So for example, you take this query. I'm taking a select from one table, joining it with another table. It gets fed into this thing called Catalyst. So Catalyst is the module within Spark that does all of this parsing and optimization. And out at the end, you end up doing distributed work. So what's really happening in here? A lot of people take a look at this and just kind of pass. Like, I don't really need to know what's happening on the inside. What's really more important is that I get this output that I want. But today we're going to talk a lot about how the internals of this work, so we can figure out how we can actually change them and have it behave in different ways that might be more beneficial to specific data sources. So let's take a little example here. This is some actual compiling Scala Spark code. And imagine we have these two tables, and we want to perform a join between the two of them. So we basically make a reference to each of those tables. We can do some filters. We're looking for in this particular join, we're looking for things where the visit ID is greater than 1, where the cost was more than 10. We want to join these two databases because one has which dogs a person owns, and the other has some information about their billing, when they went to the vet or not. And we need to mash this together so we can figure out which dogs were at which visits or something like that. So we do this description here, which looks a lot like SQL. There's actually an SQL description of this that you can write as well. But this is the Scala API. And in the end, it's going to give us the results we want. But under the hood, what's happening? So the first thing that happens is that code, that Scala we've written, gets transformed into a tree, a parsed tree. So all of those operations end up being represented as specific classes. So we've got this join thing, these filters, these relations that we're pulling data from. And we can actually look at all these and kind of classify them by type. So this tree says, in order to do this amount of work, what we need to actually do is we have to perform a join. The join requires this owner column number 9 and owner column 224. To get those columns, we need to do projections off of some table that we're reading information from. And we have these filters. So these filters happen in certain places. And this is basically a big explanation of what needs to happen to get the answer to this request. So it's pretty important to realize that at this level, at this stage of optimization, really what we're focused on is what needs to happen, not how does it need to happen. Because actually figuring out the how of it is going to be a little more complicated, and once we're at that stage, it's a lot harder to make optimizations. So each of these nodes in this plan is what we call a logical node, because it is a logical description rather than a physical description of what is happening. These nodes are built pretty simply. So they have, a class which extends logical plan. In this case, this is filter. Filter extends logical plan. Each logical plan node has an output, tells us which columns are coming out of it, which columns are produced by this. And we have a set of children, which is what are the things that happen before this. So for example, this filter is applied to another tree, and that tree consists of a filter and a relation. So inside of that, we still have to describe this actual filter itself, which is that we're looking at this cost column and we're looking for it to be greater than 10. So that actually is what we call an expression, which is also going to become a tree. And this is in another class in the expressions. So all of these extend expressions now. And they can have things like this reference right here is a greater than. And the greater than, of course, has two children, one for each side. In this case, one of these is a reference to a value in a tree, or a value in a table. And the other is just the literal number 10. So we have this tree, and inside of our tree we have more trees, but basically everything is structured where we have this very clear definition of what needs to be done to accomplish this logical part of the query. So looking at it from a much higher level view, every logical node is a definition of some inputs that get changed by some set of expressions that produce some set of outputs. And if you know these input and outputs, you can make a lot of choices about the order of things. You can decide whether or not a certain node can be in a certain place, or whether you can move it up or down within that tree. Because, for example, if I'm doing a filter, well, there's no reason that one filter has to happen before another filter. We can always swap their order and get the same result. So if we can do those sorts of things, we need to have rules that explain how do we swap these things? How do we move them around? How do we check whether any of this is valid? So this logical plan then goes through a set of optimizers. So there's two phases which change the logical plan tree, but they change it into yet another logical tree. So in this case, these phases are the analyzer phase and the optimizer phase. And we'll just go briefly through what those do so we can get an idea of why we might want to add things in those places. So to change a logical tree, we use something called a rule. And this is just the definition of the rule class in Spark. And what you'll see is what the rule does, all we have to do is we take in one tree and we output one tree. That's all a rule has to do. It can do whatever it wants inside of that, but what it really needs to do is take in a tree, do something to it, and output another tree. So rules can be applied in a bunch of different ways. So for example, this is a bit of code showing you that there's a certain set of rules that they've labeled substitution, the C to E substitution, window substitution, eliminate unions, all of these things. And the way Catalyst can apply these rules is based on a parameter here. Here it's fixed point. Fixed point means keep applying this rule over and over and over until the output matches the input. There's other options. You can set it to only apply a rule one time or only apply a rule n times. But in this case, we basically say we'll just keep applying the rule over and over until it doesn't work anymore. So this is good for things like recursive rules where we might eliminate, for example, we might eliminate a union, but that then provides us with a new pair of expressions that we can also eliminate. So we would keep applying it over and over till we've gotten out of that state. So just to go over examples of what analyzer rules look like, this is that first stage of logical plan optimization. Here's a list of all the ones that are currently in Spark 2.3. Don't worry about that. The thing in general is that analyzer rules are all about saying, is this even possible? Are the things you're calling real? So for example, you called a UDF in the middle of your code that is called Bob's UDF 5, right? So it needs to check within the catalog. It needs to check within Spark to say, is that a real function that exists in this scope? Can I actually do something with that? Or you might recall on a table. And to call on a table, it has to go then check in the catalog and see, does this table actually exist? So it's all those kinds of rules. It's like, are you looking for columns that exist? Are you looking for tables that exist? So this phase is basically our first sanity check to make sure that this query is at least reasonable. At least we're talking about things that the engine knows how to handle. Here's an example of 4. I've done a nice clickbait title here, just so you might want to look at 4. It's not really anything special, but like I was saying, we're making sure that we have relations that exist inside of our catalog. We're making sure our functions are real. We're making sure that if we used a star or we've aliased a column as something else, that's valid. So that if we select a column and maybe rename it as something else, we select column X and rename it to Y, we need to make sure later on that all of our Y references can be mapped back to a real X. So that's the kind of checks that are happening in this analysis phase. So here's an example of one of those rules in action. So this is that eliminate unions I was talking about before. So this is basically just saying, if I'm doing something, if I'm trying to do a union, and there's only one thing in my union, then I really don't have to do anything at all. So take that tree that has a child and just take the child. So you can imagine now this is why I would want to apply this rule over and over and over again, because if, for example, I say I would like to take the union of this, and then I'd like to take the union of that, and you can keep wrapping this over and over and over, but logically it's all the same thing. A union of one object is the same as just that object. So you can keep unwrapping them until you end up with a single child. So this is the actual code for that eliminate union. Like I said, basically says if you've got one child, then take the child. That's it. So the more exciting rules are our optimizer rules. So this is that second stage of the logical plan analysis. So in the logical plan analysis, we want to make things better. We aren't just trying to check whether or not functions exist or catalogs or tables exist. Now we're really interested in, can we do it better without actually knowing how we're going to do it? So I know that might sound a little confusing, but let's just go over some examples. So again, I have another clickbait title. Here's 5 examples. For example, if we have a limit inside of our logical plan, there's almost no cases in where if we can move that limit closer to the actual read or closer to the source of data, it's almost always going to be better. So we have a rule that says if you have a node that's limiting the amount of results, keep moving that down as far as you can in the plan so it happens as quickly as possible. Another one like constant folding. If you're in your application and you do a request that's select whether or not column X is greater than 1 plus 1, well, computers are very smart and good at math, so they might as well just do greater than 2. Because why calculate 1 plus 1 every single time you're comparing a row? So this would take 2 different nodes that are part of that addition, so it probably would be add literal 1, add literal 1, and combines them into literal 2. Another one, combine filters. Imagine you have multiple filters that are on a single column. It probably helps to combine them all into a single logical node so that things down the road can actually take that full set of expressions and do something with them rather than assuming there's just one at a time. Cost-based join reorder. This is one where it can actually look at the underlying stats. If you've looked into the cost-based optimizer in Spark, this is the node that basically says, okay, this join should probably happen before that join because this join is going to require less data and will mean that the second join will end up being a lot more efficient. And at the end, there's a rule like simplify casts. So casts are UDF. If I have to change from one data type to another data type, that can be expensive. But if I already have an integer and I try to cast that into an integer, well, just remove that. Just remove that entire operation so we can actually save time by getting rid of things that don't need to be done. So here's an example of how that unneeded cast rule actually works. So it's, again, like the other rules we looked at, it takes a logical plan, outputs a logical plan, and this one just looks at whether or not you're casting a column to a data type, and if the column's data type is the data type you're casting it to, we remove that whole node. There's some other specialty things here because you have in complex types, this becomes a little more complicated, but I just wanted to show this part because it's very easy to understand that if we have the same data type that we're looking at, just get rid of it. So for example, this projection with a cast inside of it can be changed just to the projection of that column because in the case that A is an int type. So we just remove that extra bit of work. So again, these are all talking about what needs to happen. What kind of operations need to happen before our query actually can be executed. The hard part of this, of course, is none of this talks about how to do this distributedly. None of this says actually how to do the math, how to do the programming that actually will take our rows, put it through all of this, and give us a result set. Now for that, we have to also, first we apply all of our rules and we get our optimized plan. Like I said, we combine our filters, all that kind of stuff. But we need to turn this into a description of what's happening. What do we actually have to do? Does this relation mean that we actually have to read data out of Cassandra? Or does this mean we have to get data out of JDBC? Does that mean we start a connection pool and start pulling out rows one at a time? Like, we actually have to figure that out before we can do any work. So that's what the last transformation inside of Catalyst is, and that's the application of strategies. This is the planning stage. So the planning stage is different than the other stages before this because it takes us from a logical plan into a Spark plan. Spark plan is part of a physical plan, which is a description of the actual code we will be running one row at a time to actually get results. So an example of what this actually means in practice is something like this. So for example, if I have a join between a column A and a column B, well, we know what a join looks like when it's done, but how do we get to that phase? So in Spark, there's a bunch of options. So for example, it could do a sort merge join. This is where it takes the tables and it writes out many subfiles, and those subfiles get shuffled all around, and then they get merged back together, and we do a join that way with this big distributed shuffle operation. It's very expensive. We have another option called a broadcast join. A broadcast join in Spark takes one side of the join, takes it into a map, parallelizes that to every executor, and then just does a lookup within that map. So deciding which of these you're going to actually do, you can see this is the actual physical thing. What are we actually going to do to get the answer is a pretty important choice. We have to decide which of these we do. And then on the other hand, we have these relations. So remember I said we had that logical relation at the bottom that refers to something in the catalog or some other kind of source. Well, we have to turn that into code that actually takes data out of that source. So for example, logical relations, if you're familiar with Spark, you can do Spark read format CSV, or read format Parquet, or read format Cassandra. That will then get transformed into a physical piece of a physical reference to one of the data sources that actually reads data out of those various external third-party things. So one little issue here you might have noticed is that if we're writing these plans that take a logical plan and turn them into a Spark plan, we kind of have a problem applying them piecewise, because if we want to apply something over and over again, we can't really do that, because once we've applied the rule once, we should end up with a Spark plan. We shouldn't end up with a logical plan. So we can't apply the same rule over and over again. Well, the way that Spark gets around this is that one of the things you do when you're writing a rule, so this is a lot of the internals, is anything that you're not taking care of in your planner rule, you wrap around with a plan later. So plan later makes this into a physical node. But it's a physical node that actually just gets wiped clean every single time we go through it, so we can actually do something over and over again. So say, for example, I don't know how to deal with the join in the rule that I've written, but I do know how to deal with something else. So I can handle that part and change that into physical nodes. And then for all the things that I don't understand, that I don't know how to work with, I just wrap them in a plan later. So then that will get back into the planner again, and the planner will be able to unwrap that and try again with other rules that are within that set of planning rules. So here's a quick example of what's inside these Spark plan nodes. So again, we actually have a node that also just says filter at the front, but this is execution filter exec. So inside of the Spark code base, if you take a look, all of these physical nodes have these exec preferences or suffixes, and they extend a whole lot of other stuff. And this is where a lot of the cool things in Spark actually come into play. So we'll go through a little bit of that. So, for example, since this node has is a filter exe, it has a doExecute method. So this is where we actually have the code to deal with a row. You'll notice we can take an RDD of rows here, and we can actually do something on them. The first thing it does is, of course, call its children and has them do whatever they need to do. And then it takes the iterator that comes out of that, and you'll notice it takes the predicate that is inside of this, makes an operation on it, and then iterates all the rows coming through with the predicate. So basically, this is the literal code that will be evaluated every single time you go through a filter step inside of your job. But you've probably heard a little bit about how Spark now has a whole lot of cool code gen stuff. It's actually going to compile new code when you write a plan. So how does that come into play? So if you notice up here, there's another thing extended here called code gen support. So code gen support gives you the opportunity within this execution node to give these two other methods, do produce and do consume, which basically let you say what code needs to be generated if this node is in place and code gen is enabled. So instead of saying how to work with a row, it actually expects you to produce a string which literally has the code that would be run, that will be added to the compilation for the large code gen section. So again, this is a lot of the internals, but this is how it actually happens. So if you put a whole lot of these nodes together, it will use all of these do produce and do consume nodes to get strings of code that it will put into a class file and then compile. So that's how we actually get the how to work with it even when we're doing code gen. Again, this how has to be fully explained here. We have no other stages after this which will say how to work with a row, how to actually deal with the data we're working with. So this is the bottom line. Whatever is in here is what actually happens. So what kind of planner rules are there? So there's a whole lot of different kind of planner rules. This is actually it. This is the whole list. I'll just go over a few of the ones that are really relevant to me as someone who writes the Spark Cassandra connector. Filter pushdowns is one of the planning rules because there's a point now where we have this logical relation that says we need to do a filter on this column, but we also have this relationship that says we're pulling data from somewhere else. This is the case where we can actually look and say, oh, okay, that particular predicate can be handled inside of that source now that we know that the source is actually Cassandra, because Cassandra has certain rules about what filters you can use. Other things like column pruning. If we can tell that we don't need all of the columns out of the source, we can actually tell that base relationship, don't read all those data, don't read all those different columns. And of course, all of the other stuff where we write how things actually get written to the data source and how we make the connection pools and all of that. All of that stuff gets happen when we apply these rules. So we go from our previous optimized logical plan into this physical plan. So this is the physical representation of the same plan we were looking at before. You'll see a lot of this is a little different. There are a few things that you probably want to see when you're doing your own requests and you do an explain. You'll notice that you've got these stars on some of these methods. The stars all represent a place where code gen is happening. So this shows us that it's not using those do execute methods. Instead, it's actually producing that code and compiling a new class that will run through my data. It also shows us now a lot of important information about what filters have been pushed down to the database, what are the actual rows we're reading out of the database, all that kind of stuff. So we actually get a much clearer prediction of what's actually happening. And in this case, we can tell that the join we're doing here is a sort merge join. So it's decided that both of these tables are large enough, based on the size estimates that they've given, that it does not want to do a join based on a broadcast. So you can actually tell why this would be much slower than a different plan based on the operations that it's doing. So what I wanted to talk about, given all of this information, is how can we make this better? How can we add into this framework? So one thing I know about Cassandra is Cassandra has really fast key lookups. It's very good at looking up one key at a time very quickly, as long as it has the partition key. So there's some kinds of joins we can do then we can do much more efficiently than actually doing a sort merge join or even a broadcast join, because we don't have to fully scan the Cassandra table. We can instead take those partition key values and pull them out directly. So we added something called direct join. And this is a feature that we've done quite recently. And to actually accomplish this, to actually make that new relationship, what we did is we made a new physical node, a new planning node. Because like we talked about before, the issue we want to change here is not the what needs to happen, but we want to change how it happens. So now instead of there just being an option to do a sort merge join and a broadcast join, we added another option called a DSE join. So the DSE join is going to be very similar. It's going to contain a join condition. It's going to contain which columns it needs to read out, how it needs to read them out, and it's going to have children. The children will be the source of the keys that it's using to pull things out of Cassandra. So instead of the plan we saw before, we end up with a plan that looks like this, where we don't have a shuffle, because we don't need to do a shuffle. We know how to pull those keys directly out of the database. And we only have one branch beneath it. So basically, whenever you're looking at a Spark plan and you see two branches coming out of something, that usually means you're about to do a shuffle or some kind of join. So this ends up being much more efficient. I'm running a little low on time, so I'm going to quickly go how we do this. Basically, we take the plan we had before, this logical plan. Remember, this is before we go into that physical planning stage. We look for which of the sides of this are smaller. We check the sizes that are estimated to come out of both sides of this branch. We look for one that's really small. We check whether or not it is significantly smaller than the other side, because we don't want to join, if for example our database has 1 million keys in it, and you're looking up 100 million values, then it makes much more sense to just read the entire thing before checking. But if you're only looking up 10,000 keys out of 1 million values in the database, then it makes much more sense to do this kind of direct lookup. Just look up 10,000 values rather than reading every single one. So we look for the smaller side. We take that branch and we kind of smush it together. We take all of the nodes that existed on that path in the logical plan, and we combine them into a single node. So we basically extract the information out of all of those and make the corresponding direct join physical node. Now, like I said before, one of the challenges here is that we don't know how to deal with the rest of it. We don't know how to deal with what happens before this join happens, and we also don't know what happens after this join happens. So you might be doing this join operation and then a whole lot of other things with the results. We're not doing anything with that, so we wrap that, both parts, in a plan later. So once we've done all that, we end up with the final plan that I showed you before. We have this nice little tight direct join here, and we have our other table that we're doing a full scan on to pull out of Cassandra, and we get the same results we would have gotten if we had done a sort merge join. So just to show some motivation as to why this was really important, this drastically improves our join speed. So this is on a database that has 4.5 billion rows in it, and these are all in the 100 million, so just, you don't have to count the zeros. It's 100, 200, 300, 400 million. But if we're looking up one of these smaller subsets of keys out of the total number of rows, we can actually do that much faster, orders of magnitudes faster than if we just scanned both sides and then did a sort merge join. The yellow line here is this time for the entire Spark merge join, where the red line here is the time required just to read the entire table out of Cassandra. So we end up saving a ton of time by optimizing this join, and we can do it all automatically. So that's basically what I wanted to talk about today. I'd be glad to answer any questions you have on adding rules to Catalyst or how Catalyst works. Thanks for coming, and of course, if you would like to know more about what we're doing, you should join Datastax, where we're doing all kinds of fun things like this. All right, yeah, questions?
So like 2 questions. The first one is, just recently I found that on Hive, okay, not on Spark, I have to test it on Spark. Select, count, distinct on multiple columns, so as a key, works slower than select, count everything from, and then in the parentheses you do select, distinct, everything. So the second one works much faster. Okay, this is on Hive. Another question is somehow when I did some SQL with the parentheses, calling SQL, Spark SQL, worked less efficient, probably, I don't know, 3 orders of magnitude than if I did through the dot notation. It involved filtering and joins as well.
So one thing that is quite particular between the two APIs right now is the order of joins. So by default, Spark does joins in the order in which you request them. The cost-based join optimizer is a pretty late feature. It's experimental. You have to turn it on explicitly and do calculations of statistics before. So that might be the difference, is that if you say that there are certain joins, it will not reorder those joins. It will do the joins in the order that you have given them. Because that's one of those things where to actually do a good reordering, it needs statistics on like the cardinality of the keys and the total amount of data. And if it doesn't have that information, it's just like, well, whatever you gave me is what I'm going to do. So that's usually the difference. Underlying both methods, the Scala.api and the Spark SQL, just the SQL string API, they use the exact same optimization engine. So there should be a one-for-one matching between every SQL string you can write and every Scala API. The problem is you do get situations like that where parsing a string could represent a slightly different order of operations that may screw up the join order or something like that. So that would be my guess. It also sometimes has issues with casting. Because you've written everything as a string in Spark SQL, it doesn't know if your literals are the correct type. So it usually, if you haven't written them out explicitly, assumes every literal is a string and then casts the other column to a string before it does a comparison. So that's something to watch as well. So you had one more question, and then we can go. It was on distinct. I don't know about the behavior in Hive. I know in Spark, the difference between like a count with a column and a count all by itself is whether or not those columns are going to get passed through all the way to the source. So if, for example, you ask for something that requires no columns, it will actually end up at the relation and tell the relationship, you don't actually have to count and read any data out of the database. All you need to do is tell me how many rows there are. So that can actually switch up performance significantly. We've seen, we actually had an issue before where in Cassandra, if you did a select count some column versus select count all of the columns, you would get, or select count versus no columns, you would end up with a very different execution because selecting one column would prune it down to requesting only a single column out of Cassandra. But we hadn't programmed it that if you asked for no columns, it should get no data. It should just return the row count. So we ended up adding that as a later optimization. So now if you ask for no columns, it actually asks for no columns, where before no columns was the same as all columns, and one column was then much better than no columns. So little things like that. Yeah?
I don't know if you went through it deeply, but how does the connector, how do you register that you have like these new node types or this new data source type?
Yeah, so to register new data source types, so there's two different things. So if you want to add new nodes, this is a little more complicated. This is where there are a few extension points. If you want to do it, you can do it live at the Spark session. So Spark session has inside of its builder apply extensions, which lets you pass in a lambda that given your session state, I believe you can pass in more functions or you can pass in more plan nodes or analysis rules, all that sort of thing. What we use, since we're selling the software to folks who don't really want to get into the nitty-gritty of it, we want to preload all of those functions and extensions into our distribution. There's a Spark, I'm going to forget the exact parameter name, but it's something along the lines of spark.sql.extensions, which lets you provide a class that will be loaded via reflection, which is allowed to add functions and analysis nodes and planner nodes and things like that. So that's separate than data sources. If you want to add a new data source, it's actually a lot easier. Data sources follow a different API that doesn't require knowing about all of this stuff. You basically have to just describe, given a read, how do you get that data out? Given these column requests, how do you get those columns? You don't actually have to think about the expression trees and how it's going to fit in the optimizer. It does all that for you. So for that, you just make your class, and then a user has to have it on the class path and refers to it by package name.
I see. So to be clear, it is Spark's Catalyst engine that is loading your provided node types and then using it in its own.
Yeah.
Okay.
So I know it's hard to see because I had them all listed in very tiny text, but basically it adds them to the bottom.
Yeah.
So is this at the end kind of doing like a map partition from one of the table to the other?
If you do code gen,
Yeah.
it will end up doing a map, an ORDD map partition with the generated code.
Okay.
So in our case, we are not doing code gen in this implementation yet. We're just using that do execute method, so it actually takes an internal row and then does a map partition, but it also still just does map partition.
So
Yeah.
maybe you talked about it, but do your optimization rules in Canvas, do they make use of statistics you have in Cassandra? And then how do you access them?
So right now, we make use of the size estimates table in Cassandra. So Cassandra gives a very rough estimation of how much data is inside of it. It's not very accurate, but that's basically all we have at the moment. We're working on trying to get some cardinality and other information embedded into SS tables so we can do better. But yeah, so since this code, like I showed you, basically lets us do whatever we want inside of it. So we basically put inside of the actual planning rules. The planning rules make a connection to Cassandra, look at the underlying table that it's checking, and pulls out that estimate data.
Cool. So it's not, you don't push it into the Spark catalog and get it from.
We don't push it into the Spark catalog.
Okay.
Any other questions? I think we have like 4 minutes. Yeah?
So if you're doing a lot of repeated queries of the same types of data or whatever, and you keep running these optimizations every time that you launch it, is there anything you've experimented with where you remove certain rules that you know never apply to the workload that you're doing? Does that have much effect?
So within the Spark Optimizer, unfortunately, it can't tell whether or not they were really important while it's running. So that's not something that's part of the optimizer right now. It's actually pretty far away from a cost-based optimizer, which is what you would need to do. You basically need to collect statistics every time something runs and make sure those are stored somewhere. The best thing that it can do at the moment is that if you run the same query more than once, it does cache a lot of that. So it'll be like, oh, you're requesting to do this thing that you just did. Well, we actually know how that optimization played out. It's not changed. So yeah.
One more question about
Yeah,
the
sure.
development. So when Spark, so how do you maintain your changes relative to changes upstream?
With difficulty. I mean, what you have to do is you just have to keep up. Every time Spark changes internals, we have to change with them. We have to keep up. I mean, this is pretty typical. So one of the things that's currently in development within Spark is the data source. The data source v2 API. So basically the data source API, that easier way of incorporating your readers and writers into Spark, is being revamped because one of the big changes with allowing continuous stream processing, where you have that per tuple based processing, is that the methods that you expose in the data source API are really not sufficient, because you have to suddenly deal with the fact that a record is going to go through the system not in a batch, but one at a time. So there's a whole new API that's being developed. It's being worked on right now. It's not quite finished, but it allows for a lot more specifics on that sort of thing. Like you've just gotten 10 rows, write them, rather than you've just gotten an RDD full of rows, write all of those. Another cool thing that's that's coming in data source v2 is that currently there is no way of a data source exposing the internal clustering of the data that's being read. So in Cassandra's case, things that share the same partition key are on the same physical machine. So if you do a read of data, then a group based on that partition key, we are already guaranteed that our partitions, our Spark partitions, all contain, they're basically organized by key already. And since they're organized by key already, we shouldn't have to do another shuffle before we do our reduce or our group by. So that's one of the cool things in Data Source v2 is we can actually expose that into Catalyst, so Catalyst can make smarter decisions about, do you really need to do a co-grouping before you do this operation?
So other thing I was interested in is how does the data locality kind of works with the Cassandra connector?
So within the Cassandra connector, so I didn't go over this in this talk, but this is basically the way we do it is if you imagine Cassandra has a token range, and you can think of that as a long line that lists all of the possible data that's in the database. We cut that into sections based on the ranges that are actually replicated within the database. So this happens every time you do a full table scan. So it'll basically say this range belongs on this node, this range belongs on this node, and then it will cut those up into pieces that match the expected size that you want of how much data you want in every Spark partition, and then attempts to execute those on executors that have the same IP address as the replicas for that token range. So basically, if you're looking for tokens 1 through 10, and you know tokens 1 through 10 are on nodes 1, 2, and 3, it looks for executors that are 1, 2, and 3, and attempts to run the task that reads that particular token range on those nodes. Yep. Well, I think that's my time. I was told there's no runners, so I have to shut it down. So thanks a lot.